There is a wall 16 billion light years away and you will never cross it. Not because we lack the technology, not because we need faster ships or better telescopes. You cannot cross it because the universe itself forbids it. Space beyond that boundary is expanding faster than light can travel. Galaxies out there are moving away from us at speeds that make their light Yongyuan unreachable. The photons they emit today will never arrive. They are trying to reach us, racing through the void at maximum speed, but the space between us grows faster than they can cross it. This is not science fiction. This is physics. The wall of light is real, and it is stealing the universe from us right now. 94% of all galaxies that exist have already slipped beyond this boundary. Their light will never reach Earth. Not in a billion years, not ever. If you want to understand why we're trapped inside an invisible prison that is shrinking every second, hit that like button and subscribe. Prepare yourselves. We begin. Light moves at exactly 299,792,458 meters per second. This number is not arbitrary. It is the maximum speed at which any information can travel through the universe. Nothing moves faster. Not particles, not energy, not information of any kind. This speed limit is absolute, woven into the fabric of space-time itself by the laws of physics. Einstein proved this in 1905. His special relativity showed that light speed is the same for all observers, regardless of their motion. More importantly, he showed that reaching light speed requires infinite energy. The faster you go, the more energy you need to accelerate further. As you approach light speed, your mass effectively increases, requiring ever more energy for each additional increment of velocity. At light speed itself, the energy requirement becomes infinite. The universe simply does not allow it. This creates a fundamental constraint on everything that happens in the cosmos. When a star explodes on the far side of the galaxy, we do not see it instantly. The light must travel the distance between us at this fixed speed. If the star is 10,000 light years away, we see the explosion 10,000 years after it happened. We are not watching the event itself. We are watching its ancient light finally arriving. This delay is not just inconvenient, it is structural. Every observation we make is an observation of the past. The farther we look into space, the farther back in time we see. The sun we observe in the sky is 8 minutes old. The light left its surface 8 minutes ago and only now reaches our eyes. If the sun vanished right now, we would not know for 8 minutes. We would continue seeing it, continue feeling its warmth, completely unaware that it no longer existed. The nearest star beyond the sun, Proxima Centauri, is 4.2 light years away. When we look at it through a telescope, we see light that left that star 4.2 years ago. We have no idea what Proxima Centauri is doing right now. It could have exploded 3 years ago, and we would still see it shining peacefully in the sky for another year. The concept of now becomes meaningless across cosmic distances. There is no shared present moment between us and distant objects. There is only the past, frozen in the light that finally arrives. For nearby objects, this delay is manageable. We can wait. If something changes on Proxima Centauri today, we will find out in 4 years. The information will eventually reach us, but as distances increase, the delays become more than just waiting periods. They become barriers. A galaxy 1 million light years away shows us what it looked like 1 million years ago. We see its ancient structure, its stars as they were when early humans were just beginning to walk upright on Earth. That galaxy has spent 1 million years evolving, changing, possibly colliding with neighbours or forming new stars. We know none of this. We cannot know it. The information describing its current state is still travelling toward us through the void, and it will not arrive for another 1 million years. This light travel time creates the first boundary around us. We can only observe objects whose light has had time to reach us since the universe began. The universe is 13.8 billion years old. Therefore, light from objects more than 13.8 billion light years away has not had time to arrive. Those regions are invisible not because they do not exist, but because their light is still in transit. We are waiting for information that is already on its way. But this is not the wall. This is just distance and time doing what they always do. The light from those distant regions will eventually arrive. We just need to wait long enough. The real problem, the true barrier, emerges when we account for what the universe has been doing during those 13.8 billion years. Space itself has been expanding, and that expansion changes everything. In 1929, Edwin Hubble pointed a telescope at distant galaxies and discovered something that shattered every assumption about the cosmos. The galaxies were moving, all of them, away from us, and the farther away they were, the faster they moved. This was not random motion. It was a pattern, a relationship. Double the distance, double the speed, triple the distance, triple the speed. The universe was not static. It was expanding. This was not galaxies flying through space like shrapnel from an explosion. This was space itself stretching, carrying galaxies along with it. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart. But no dot is actually travelling across the rubber. The rubber itself is expanding, and the dots are just embedded in it. That is what space does. It grows. And as it grows, everything embedded in it gets pulled apart. The expansion is uniform. Every region of space expands at the same rate. This rate is called the Hubble constant, and its current value is about 70 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light years. So for every 3.3 million light years of distance between us and a galaxy, that galaxy recedes at an additional 70 kilometers per second due to expansion alone. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. The relationship is linear and relentless. At close distances, this expansion is negligible. Gravity between nearby objects is strong enough to hold them together despite space trying to pull them apart. The Milky Way and Andromeda are gravitationally bound. They will eventually collide regardless of cosmic expansion. Our local group of galaxies forms a stable structure because gravity dominates at these scales. Expansion does not tear apart solar systems, galaxies, or even galaxy clusters. It only affects the vast spaces between these structures. But at truly cosmic distances, gravity becomes irrelevant. There is not enough matter to hold anything together. Expansion takes over completely. And because the expansion rate depends on distance, there exists a critical distance where the recession velocity equals the speed of light. Beyond that distance, space expands so fast that light itself cannot make progress toward us. Calculate that distance. Light speed is roughly 300,000 kilometers per second. The Hubble constant is 70 kilometers per second per megaparsec. Divide light speed by the Hubble constant. You get about 4,300 megaparsecs. That is roughly 14 billion light years. Any galaxy currently farther than 14 billion light years is receding at light speed, or faster due to expansion. Light leaving that galaxy right now will never reach us. It will try. The photons will race toward us expands faster than they can cross it. They make no progress. They are trapped, forever running on a cosmic treadmill that moves backward faster than they can run forward. This does not violate relativity. Nothing is moving through space faster than light. Space itself is expanding, and relativity has nothing to say about that. The speed limit applies to objects moving through space, not to space itself. Space can expand at any rate, and in distant regions it expands fast enough to create an insurmountable barrier. But the situation is worse than this. Much worse. Because expansion is not constant. It is accelerating. In 1998, two independent teams studying distant supernovae discovered that the universe's expansion is speeding up. This was completely unexpected. Gravity should slow expansion over time, not accelerate it. Something was pushing space apart with increasing strength. Cosmologists name this mysterious force dark energy, and it makes up roughly 68% of the universe's total energy content. We do not know what it is. We do not know why it exists, but we know what it does. It makes expansion accelerate. This acceleration has catastrophic consequences for observability. In a decelerating universe, regions currently receding faster than light might eventually slow down enough for their light to reach us. We could wait them out, but in an accelerating universe, those regions speed up. They recede faster every moment. Light that is already struggling to reach us falls farther behind, and regions that are currently within reach will eventually accelerate beyond the light speed threshold and disappear from view. Dark energy is not just expanding the universe, it is closing a door, permanently. Every second, more galaxies slip beyond the boundary where their light can never reach us. Every second, the observable universe shrinks in terms of what we can ever hope to see. The expansion creates a horizon, and that horizon is moving inward in moving coordinates. We are losing access to the cosmos in real time. The balloon analogy breaks down here because balloons do not accelerate their expansion on their own, but the universe does. Imagine the balloon inflating faster and faster, with no limit to how fast it can grow. Dots on opposite sides of the balloon eventually move apart so quickly that light cannot cross from one to the other. Those dots become causally disconnected. Events on one dot cannot influence the other. Information cannot pass between them. They exist in separate, isolated regions of space-time. This is not theoretical. This is happening right now. There are galaxies out there, real galaxies full of stars and planets, whose light is currently en route to us but will never arrive because space is expanding too fast. The photons are redshifted to longer and longer wavelengths, losing energy, stretching into invisibility. Eventually they redshift to infinite wavelength. Effectively, they cease to exist as detectable particles. The information they carried is lost. The universe is not just big, it is not just expanding, it is accelerating away from us so fast that most of it has already become unreachable. Therefore, the wall we are discussing is not made of matter or energy. It is made of motion. It is the boundary beyond which space itself moves faster than light can compensate, and it is shrinking. The farthest light we can currently observe comes from galaxies whose photons have been travelling toward us for 13.8 billion years. That light left those galaxies when the universe was very young, shortly after the Big Bang. During that journey, space expanded continuously, stretching the distance between us and the source. By the time the light arrives, the galaxy that emitted it is no longer where it was. It has been carried away by expansion. The current distance to that galaxy is not 13.8 billion light-years. It is approximately 46 billion light-years. This distance defines the particle horizon. It is the radius of the observable universe. Everything within this sphere has had enough time since the Big Bang for its light to reach us, accounting for expansion during the light's travel. Everything beyond this sphere has not. The photons from those regions are still in transit, racing toward us but not yet arrived. We cannot see them yet, but we will, eventually. As time passes, the particle horizon grows. More distant regions come into view as their light finally completes the journey. This sounds reassuring. It suggests we are not trapped. We just need to wait longer, and we will see more. The observable universe will expand. Our view will deepen. We will gain access to previously hidden regions. But this is an illusion. The particle horizon describes what we can see now. It does not describe what we will ever be able to see. Those are two different boundaries, and the second one is far more restrictive. The particle horizon grows because the universe has a finite age. Light has only had 13.8 billion years to travel. As the universe ages, light from farther away gets more time to reach us. In principle, if we waited forever, the particle horizon would grow to infinite size. We would eventually see everything. But this assumes the expansion rate stays constant or slows down. It does not. It accelerates. An acceleration changes the geometry completely. When expansion accelerates, distant light does not just get delayed, it gets trapped. Photons emitted beyond a certain distance never arrive, no matter how long we wait. They are stuck in a region of space that is receding faster than they can approach. This creates a second horizon, fundamentally different from the particle horizon. It is called the cosmic event horizon, and it defines the boundary of what we can ever observe, even if we wait infinitely long. The cosmic event horizon is currently located at roughly 16 billion light-years in comoving distance. Comoving distance is a coordinate system that factors out the expansion of space, measuring where an object is now rather than where it was when it emitted the light we see. Any galaxy currently beyond 16 billion light-years will never send us light that arrives. Not today, not in 1 trillion years, never. The light it emits will perpetually lose ground to the expanding space between us. It will redshift toward infinity and fade into undetectability. This boundary is not moving outward like the particle horizon. It is effectively fixed in comoving coordinates, and in some measures, it is shrinking. Galaxies that are currently just inside the horizon, barely reachable, will cross the threshold and disappear. Their light will stretch beyond detection. Future astronomers will point their telescopes at those regions and see nothing. The galaxies will still exist. They will still emit light. But that light will never complete the journey. Think about what this means. There are galaxies we can see right now, faint smudges at the edge of our instrument's detection limits, that are already beyond the cosmic event horizon. The light we are receiving from them was emitted billions of years ago when they were closer, before expansion carried them past the threshold. We are watching their past selves. Their current selves are invisible and always will be. We have already seen the last light we will ever receive from them. Every observation we make is a farewell. The cosmic event horizon is not like the particle horizon. The particle horizon is a statement about the past. It tells us what has had time to reach us. The cosmic event horizon is a statement about the future. It tells us what will ever be able to reach us. And because expansion accelerates, the future is far more limited than the past. We have access to less of the universe going forward than we did looking backward. This creates a disturbing asymmetry. Early in the universe's history, when expansion was slower, the cosmic event horizon was much larger. Objects that are now beyond our reach were once within it. Light from those objects had time to arrive before acceleration made the journey impossible. We can still see that ancient light, but no new light from those objects will arrive. We have a snapshot of their distant past, frozen in the photons that barely made it across the threshold before the door closed. Everything that happened to those galaxies afterward is hidden. We watched them for a brief window in cosmic time, and then they vanished behind the wall. The numbers are staggering. The observable universe contains roughly 2 trillion galaxies, but the vast majority of those galaxies are already beyond the cosmic event horizon. Estimates suggest that 94% of galaxies we can currently observe have crossed the boundary. We see them because their light was emitted long ago, before they receded too far. But they are gone now, unreachable. We are looking at ghosts. The light exists, but the sources have moved beyond the wall, and every moment more galaxies cross the threshold. The wall is not static. It is a dynamic boundary that consumes the universe around us. Expansion accelerates. Galaxies accelerate with it. The ones currently near the edge pick up speed and slip away. Their light redshifts, dims, fades. Within billions of years, they will vanish from view entirely. The night sky will darken as source after source winks out, not because they died, but because space itself pulled them beyond the reach of light. The cosmic event horizon is the wall of light. It is the ultimate boundary of knowledge. Everything beyond it is fundamentally unobservable, not difficult to observe, not requiring better technology, impossible to observe. The information from those regions cannot reach us. It is causally disconnected. Those galaxies might as well exist in a separate universe. We share space-time with them, but we can never interact, never communicate, never learn what they contain. But the wall is not the only barrier. It is not even the earliest one. Another wall exists closer to us in time, older and more absolute, and we have been staring at it for decades. 380,000 years after the Big Bang, the universe became transparent. Before that moment, it was opaque. Not dark, opaque, filled with light that could not travel. This is the cosmic microwave background, and it represents a wall more absolute than the cosmic event horizon. Beyond this wall, electromagnetic observation is impossible. Not because of distance, because the universe itself was a barrier. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense. Temperatures exceeded billions of degrees. Matter existed as a plasma, a roiling soup of electrons, protons, and photons smashing into each other at incredible energies. Photons could not travel freely. They would move a tiny distance, collide with an electron, scatter in a random direction, move again, collide again. The mean free path of a photon was microscopically small. Light was trapped, constantly absorbed and re-emitted, unable to stream across space. This made the early universe opaque in the same way fog is opaque. Light exists within fog. It bounces between water droplets, scattering endlessly. You cannot see through it because photons never travel in straight lines for long distances. The early universe was an infinite fog of plasma, and every direction you looked was a wall of glowing particles. As the universe expanded, it cooled. Temperatures dropped. Eventually, around temperature fell below 3000 Kelvin. This is cool enough for electrons and protons to combine into neutral hydrogen atoms. This process is called recombination, and it changed everything. Neutral hydrogen does not interact with photons the way free electrons do. Once atoms formed, photons could suddenly travel freely. The fog cleared. The universe became transparent. The light that was released at that moment is still traveling through space. It has been redshifted by expansion, stretched from visible and infrared wavelengths into microwaves. This is the cosmic microwave background radiation. It fills the entire sky uniformly at a temperature of 2.7 Kelvin, just above absolute zero. Every direction we look, we see this light. It is the oldest light in the universe. It is a snapshot of what the cosmos looked like. But it is also a wall. We cannot see past it. Not with light. Not with any electromagnetic radiation. Before recombination, the universe was opaque. Photons could not escape. Any light emitted earlier than 380,000 years is trapped in an infinite series of scattering events, thermalized into the plasma, erased as distinct information. The cosmic microwave background is the surface of last scattering. It is the moment when photons were finally set free. Everything before that moment is hidden behind a glowing wall of plasma. This is not a limitation of our telescopes. This is physics. You cannot observe through an opaque medium using the same radiation the medium blocks. No matter how sensitive our instruments become, we cannot see electromagnetic signals from earlier than recombination. The universe was literally a wall of light at that time, and we are on the outside looking at its surface. The cosmic microwave background is remarkably uniform. Its temperature varies by only 1 part in 100,000 across the sky. This uniformity tells us the universe was extraordinarily smooth at that early time. Tiny density fluctuations existed, the seeds of all future structure, but they were minuscule. Those fluctuations show up as tiny hot and cold spots in the microwave background. Satellites like COBE, WMAP, and Planck have mapped these fluctuations in exquisite detail. They encode information about the early universe's density, composition, and dynamics, but they also mark the limit. The fluctuations we see are imprinted on the surface of last scattering. Anything deeper, anything earlier, is inaccessible to electromagnetic observation. We can infer what happened before recombination using physics and models. We can calculate conditions in the first seconds after the Big Bang, but we cannot directly observe those conditions with light. The wall blocks us. This creates a fundamental observational horizon in time. The cosmic event horizon is a spatial boundary, a distance beyond which light cannot reach us. The cosmic microwave background is a temporal boundary, a time before which light cannot reach us. Together they box us in. We are trapped between two walls, one in space, one in time. Cosmologists have proposed ways to peer through the microwave background wall using particles that do not interact with plasma the way photons do. Neutrinos, for example, barely interact with matter at all. A cosmic neutrino background should exist, similar to the microwave background but released much earlier, roughly 1 second after the Big Bang. If we could detect these relic neutrinos, we could see deeper into the universe's history. But neutrinos are extraordinarily difficult to detect. They pass through matter as if it were not there. Trillions of them stream through your body every second without leaving a trace. Detecting the cosmic neutrino background remains far beyond current technology. Gravitational waves offer another possibility. Gravity interacts with everything, but gravitational waves propagate freely through matter and plasma. Primordial gravitational waves generated during the Big Bang's earliest moments could, in principle, reach us today. They would carry information about the universe at times far earlier than the microwave background. Detecting them would open a window into the first fractions of a second after the Big Bang. Experiments are underway to search for these signals in the polarization patterns of the cosmic microwave background itself. No confirmed detection has been made yet. Even if we succeed in detecting neutrinos or gravitational waves from the early universe, we will only push the wall back slightly. We will not eliminate it. There are limits beyond which even these particles cannot help us. Neutrinos were only created after the universe cooled enough for certain reactions to occur. Gravitational waves from inflation, if they exist, only tell us about the inflationary epoch. They do not tell us what happened before inflation or what caused the Big Bang itself. The surface of last scattering is a wall we can see. It glows in every direction, a sphere surrounding us at a distance of 46 billion light-years in moving coordinates. It is the edge of the observable universe in time. We can photograph it. We can measure its temperature and fluctuations. We can analyze it in incredible detail, but we cannot see through it. It is opaque. And everything on the other side is lost to electromagnetic observation. This wall is older than the cosmic event horizon. It has existed since recombination. It is not growing or shrinking. It is fixed in cosmic history. No matter how advanced our technology becomes, this wall remains. Unless we develop entirely new methods of observation that do not rely on photons, we will never see the universe before 380,000 years. That era is sealed behind the glowing surface of the microwave background. Therefore, we are surrounded by walls. One wall in space prevents us from seeing distant regions. One wall in time prevents us from seeing early moments. And there is another wall, deeper still, where even the concept of observation breaks down completely. At 10 to the negative 35 meters, space-time itself stops making sense. This is the Planck length, the smallest distance that has physical meaning according to our current understanding of physics. Below this scale, quantum fluctuations in the fabric of space-time become so violent that the concepts of distance and time dissolve into chaos. This is not a technological limit. This is the point where our equations break down and reality becomes fundamentally unknowable. The Planck length emerges from combining three fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When you plug these numbers into the right equation, you get 1.6 times 10 to the negative 35 meters. This is incomprehensibly small. An atom is roughly 10 to the negative 10 meters across. The Planck length is 25 orders of magnitude smaller than that. If an atom was scaled up to the size of the observable universe, the Planck length would be about the size of a tree. At this scale, quantum mechanics and general relativity collide. General relativity describes gravity as the curvature of smooth space-time. Quantum mechanics describes reality as fundamentally uncertain and discrete. These two frameworks are incompatible. They give different predictions when applied to the same situation. At everyday scales, this does not matter. Gravity dominates at large scales. Quantum mechanics dominates at small scales. They operate in separate regimes. But at the Planck length, both become equally important, and we have no theory that unifies them. Without a theory of quantum gravity, we cannot describe what happens at Planck scales. Space-time might be discrete rather than continuous, made of tiny indivisible units, or it might fluctuate wildly, with virtual black holes forming and evaporating in fractions of a second. Or the concepts of space and time might be emergent properties that only make sense at larger scales. We do not know. Our physics fails here. This is a wall made of ignorance. This wall has consequences for cosmology. The Big Bang happened 13.8 billion years ago, but we cannot describe the moment of the Big Bang itself. As we trace the universe's history backward in time, it gets hotter and denser. Eventually, at 10 to the negative 43 seconds after the Big Bang, the universe was so dense and hot that quantum gravity effects dominated. This moment is called the Planck time. Before this, our physics provides no answers. We cannot calculate what happened. We cannot even define what before means in that regime. The Planck time is the earliest moment we can theoretically probe. Everything earlier is hidden behind a wall of quantum uncertainty. The Big Bang might have been a singularity, a point of infinite density where all known physics breaks down. Or it might have been something else entirely, a transition from a previous state we cannot describe. String theory, loop quantum gravity, and other candidate theories of quantum gravity offer speculative answers, but none are confirmed. None make testable predictions we can currently verify. This creates an absolute temporal boundary. The cosmic microwave background limits our observations to Planck time, limits our theoretical understanding to gap between these two walls, is filled with inference and calculation, not direct observation. And the region before the Planck time is completely inaccessible. It is not just unobservable, it is undescribable with current physics. Some cosmologists argue that asking what happened before the Big Bang is meaningless. If time itself began at the Big Bang, there is no before. The question is like asking what is north of the North Pole. The concept does not apply. Others propose that time is eternal, that the Big Bang was not a beginning but a transition from a previous phase. Perhaps the universe underwent a big bounce, collapsing from a previous expansion and then rebounding into the current one. Perhaps it emerged from a quantum fluctuation in a larger multiverse. These ideas are speculative. They push the wall back but do not eliminate it. The Planck length also limits what we can measure spatially. If space-time is fundamentally grainy at Planck scales, then distances smaller than the Planck length have no physical meaning. You cannot measure them because there is nothing to measure. The universe at that scale is not continuous. Trying to probe smaller distances would require concentrating so much energy into such a tiny region that you would create a black hole which would immediately obscure whatever you were trying to observe. The act of measurement destroys the information. This is a fundamental limit, not a technological one. Heisenberg's uncertainty principle reinforces this wall. Quantum mechanics forbids measuring certain pairs of properties simultaneously with arbitrary precision. Position and momentum, energy and time. The more precisely you know one, the less precisely you can know the other. At Planck scales, this uncertainty becomes dominant. You cannot pinpoint the exact location and energy of a particle simultaneously. The particle becomes a blur of probability. Space itself becomes uncertain. This quantum fuzziness means the universe at its smallest scales is probabilistic rather than deterministic. Particles do not have definite positions. They exist in superpositions of multiple states until measured. Virtual particles pop in and out of existence, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. The vacuum is not empty. It seethes with quantum activity. At Planck scales, this activity becomes so intense that space-time itself fluctuates. Distances and durations lose their classical meaning. This is the deepest wall. The cosmic event horizon prevents us from seeing distant space. The cosmic microwave background prevents us from seeing early time. The Planck scale prevents us from understanding the fundamental structure of reality itself. It is a wall built into the architecture of physics. Unless we develop a working theory of quantum gravity, this wall is impenetrable. And even if we do develop such a theory, it might tell us that the wall is not just a limitation of our knowledge, it might be a feature of reality. There might genuinely be no information about smaller scales or earlier times because those concepts do not exist in any meaningful way. We are boxed in on all sides, spatially by the cosmic event horizon, temporally by the surface of last scattering, fundamentally by quantum uncertainty. These walls are not obstacles to overcome with better instruments. They are intrinsic to the structure of the universe. We live inside a bounded region of space-time, and the boundaries are absolute. But the walls are not static. One of them is moving, and it is moving in the wrong direction. Galaxies are disappearing, not dying, disappearing. Right now, as you read this, galaxies at the edge of the observable universe are crossing the cosmic event horizon and vanishing from view. Their light is red-shifting into invisibility. Future observations will find nothing where those galaxies once appeared. They will be gone, erased from our sky, as if they never existed. This is not a slow process on cosmic timescales. It is happening continuously. Every second, light from distant galaxies stretches a little further toward the red end of the spectrum. Photons lose energy. Their wavelengths increase. Visible light becomes infrared. Infrared becomes microwave. Microwaves become radio waves. Eventually, the wavelength stretches so long that the photons become undetectable. They fade into the background noise of the universe, indistinguishable from the random fluctuations of empty space. The galaxies themselves do not change. They continue existing, forming stars, evolving, colliding with neighbours, but we lose access to them. The information they emit cannot reach us. From our perspective, they freeze and fade. The last photons we receive show them as they were billions of years ago, locked in an ancient configuration. Then even those photons stop arriving. The galaxy goes dark, not because it stopped shining, because space between us expanded too much for its light to cross. Calculations show we have already lost contact with 94% of the galaxies currently visible in our telescopes. We see them now because we are looking at old light, photons emitted billions of years ago when those galaxies were closer and space was expanding more slowly. But those galaxies have since crossed the cosmic event horizon. No new light from them will arrive. We are watching recordings, not live feeds. The galaxies we observe are ghosts. Their present selves are beyond the wall. This percentage will only increase. Dark energy continues accelerating expansion. Galaxies currently within reach will eventually speed past the threshold. The Andromeda Galaxy is safe. It is gravitationally bound to the Milky Way. The local group, our cluster of about 80 galaxies, is also safe. Gravity holds it together against expansion. But everything beyond the local group is at risk. The Virgo cluster, 60 million light-years away, will eventually recede beyond the horizon. So will the Coma cluster, the Hercules cluster, every massive structure we can currently observe. They will all fade and vanish. The timeline for this disappearance depends on the strength of dark energy. Current measurements suggest that within 100 billion years, every galaxy outside the local group will have crossed the horizon. An observer in that distant future will look out at the night sky and see nothing. No distant galaxies, no quasars, no gamma-ray bursts from the far universe, just the few dozen galaxies in the local group, isolated in an expanding void. But the erasure goes deeper than losing sight of distant objects. We are losing information. Every galaxy is unique. It has a specific mass, composition, structure, history. It contains billions of stars, each with its own properties. Planets orbit those stars. Black holes lurk at galactic centers. Clouds of gas collapse into new generations of stars. All of this is information, data about how matter behaves, how galaxies evolve, how the universe organizes itself. When a galaxy crosses the horizon, that information becomes inaccessible. We can no longer study it. We can no longer learn from it. This is information death. Not in the thermodynamic sense of entropy, but in the observational sense of knowledge. The universe contains facts about those distant galaxies, their current positions, their velocities, their chemical compositions, whether they harbour life. We will never know those facts. The information still exists somewhere in space-time, but it is causally disconnected from us. It might as well not exist. From our reference frame, it has been destroyed. The loss is permanent. Unlike information that falls into a black hole, which some theories suggest might eventually be recovered through Hawking radiation or other mechanisms, information beyond the cosmic event horizon is gone forever. There is no process that can bring it back. No future technology can retrieve it. The expansion of space is irreversible. Once a galaxy crosses the threshold, it is lost. Consider what this means for science. Astronomy depends on observing large samples of objects to understand patterns and test theories. We study thousands of galaxies to learn how they form and evolve. We observe supernovae in many different galaxies to measure cosmic expansion. We analyze the distribution of galaxies across space to map the cosmic web. All of this requires access to a large, diverse population of objects. As the observable universe shrinks, our sample size decreases. We lose access to distant galaxies that might have unusual properties or unique characteristics. We lose the ability to test our theories against a wide range of conditions. Our knowledge becomes parochial, limited to the local environment. We might miss entire classes of phenomena that only occur in distant regions now hidden beyond the wall. Worse, we lose calibration. Many measurements in cosmology rely on comparing nearby objects to distant ones. We measure the expansion rate by comparing the redshifts and distances of galaxies at various ranges. We test models of structure formation by observing how galaxy clustering changes with distance and time. If we lose access to distant objects, we lose the ability to make these comparisons. Our measurements become less reliable. Our models become harder to test. Future civilizations will face even greater challenges. If intelligent life arises in our local group billions of years from now, after all external galaxies have vanished, what will they be able to discover about the universe? They will see a small collection of nearby galaxies and nothing else. No cosmic microwave background, which will have redshifted into undetectability. No distant supernovae to reveal cosmic acceleration. No large-scale structure to indicate the universe extends beyond their local cluster. They might conclude they live in an island universe, a finite collection of galaxies surrounded by infinite empty space. They would have no evidence for the Big Bang, no indication that the universe is expanding or that it has a history. They might develop different physics, different cosmology, based on the limited data available to them, and they would be wrong. But they would have no way to know they were wrong. The information needed to correct their theories would be gone. This is the ultimate consequence of the wall of light. It is not just a boundary on our observations, it is a boundary on knowledge itself. Information beyond the wall is fundamentally inaccessible. Questions about those regions cannot be answered. Theories about them cannot be tested. We can speculate, but we cannot confirm. The wall transforms large parts of the universe into a realm of permanent mystery, and we are watching it happen. Every year, more galaxies slip away. Every decade, more information is lost. The universe is erasing itself from our view, piece by piece, light by light. We are living through an age of cosmic censorship where reality itself is hiding behind an expanding curtain of distance and time. But the wall does not just hide distant galaxies, it hides something far more fundamental. Science depends on testing. You propose a theory, you make predictions, You perform experiments or observations to check whether the predictions match reality. If they do, the theory survives. If they do not, you revise or discard it. This process only works if you can access the relevant data. The cosmic event horizon prevents that access for most of the universe. We cannot test our theories beyond the wall. We cannot verify whether the laws of physics we have discovered apply everywhere or only in the limited region we can observe. Every physical law we know is based on observations made within the observable universe. Gravity behaves a certain way. Electromagnetism follows specific equations. Quantum mechanics governs particle interactions. These laws work extraordinarily well for everything we can measure. But the observable universe represents a tiny fraction of the total cosmos. If the universe is infinite, which many cosmologists believe, then the observable portion is literally 0% of the whole. We are making universal claims based on a sample size that rounds to nothing. The assumption that physical laws are the same everywhere is called the cosmological principle. It states that the universe is homogeneous and isotropic on large scales. No location is special. The laws of physics do not change from place to place. This principle is not proven. It is assumed. We adopt it because it makes cosmology tractable. Without it, every region of space could have different physics, and modelling the universe would be impossibly complicated. But assumption is not evidence. We have some justification for the cosmological principle within the observable universe. Distant galaxies look similar to nearby ones. The cosmic microwave background is remarkably uniform across the sky, suggesting the early universe was homogeneous. Light from distant quasars passes through intervening gas clouds, and the absorption lines tell us that atomic physics worked the same way billions of years ago as it does today. These observations support the idea that physics is consistent across space and time within our observable bubble. But beyond the cosmic event horizon, we have no data. We cannot check whether distant regions follow the same rules. Perhaps they do. Perhaps the laws of physics are truly universal, applying everywhere regardless of location. Or perhaps they are not. Perhaps conditions in distant regions are so different that new physics emerges. Different values for fundamental constants, different particles, different forces, we would never know. Consider the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions. Its value is approximately 1 divided by 137. This number is critical for chemistry, atomic structure, and the behavior of matter. If it were slightly different, atoms would not form the same way. Stars would burn differently. Life as we know it might be impossible. We have measured this constant using light from distant quasars, billions of light years away, and it appears to have the same value throughout cosmic history within our observable region. But we cannot check beyond the wall. Some speculative theories suggest that fundamental constants might vary across space. In certain models of inflation, different regions of the universe underwent different amounts of expansion, creating pockets with different physical properties. These pockets could have different constants, different particles, different laws. Our observable universe would be just one pocket, one bubble in a vast multiverse where physics changes from region to region. If this is true, then the laws we have discovered are local, not universal. They describe our bubble, not the cosmos as a whole. Testing this is impossible if the other bubbles are beyond the cosmic event horizon. We cannot observe them. We cannot measure their properties. We cannot confirm or rule out the multiverse hypothesis based on observation. It remains forever speculative. The wall prevents verification. This creates a crisis for the scientific method. Science requires testability. A theory that makes no testable predictions is not scientific. It is philosophy or mathematics, interesting but not empirical. Multiverse theories, theories about regions beyond the cosmic event horizon, theories about the universe's global structure all make claims about reality that cannot be tested. They might be true, they might be false. We cannot know. The wall ensures we never will. The situation gets worse when we consider dark energy and dark matter. Together, these mysterious components make up 95 know they exist because of their gravitational effects. Dark matter holds galaxies together. Dark energy accelerates cosmic expansion. But we do not know what they are. We have not detected the particles that make up dark matter. We have not identified the mechanism behind dark energy. We have theories, but no confirmed answers. All of our evidence for dark matter and dark energy comes from the observable universe. We assume they exist everywhere, filling all of space uniformly. But we cannot check this assumption beyond the horizon. Perhaps dark energy is stronger in some regions and weaker in others. Perhaps dark matter clumps differently in distant areas. Perhaps entirely different phenomena govern those regions. We would never detect the difference. Our measurements are confined to the bubble we can see. This limitation affects cosmological models. The standard model of cosmology, lambda-cold dark matter, describes the universe's evolution from the Big Bang to the present. It makes predictions about structure formation, the cosmic microwave background, the expansion rate, and more. The model fits observations within the observable universe remarkably well, but it is a model of our local region. It might not apply globally. The universe beyond the wall might evolve according to different rules, and we would never know. Some physicists find this situation philosophically troubling. Science aims to discover universal truths, principles that apply everywhere and always. But if we can only test those principles in a limited region, how can we claim they are universal? We are extrapolating from local data to cosmic conclusions, and the extrapolation cannot be verified. We are making an enormous leap of faith, assuming that the tiny patch of space-time we inhabit is representative of the whole. Others argue this is unavoidable. We can only work with the data we have. If the universe hides most of itself behind a wall, we do our best with the accessible portion. The laws we discover might be local, but they are the best we can do. Science progresses by building models that fit observations, and if those models cannot be tested beyond a certain boundary, so be it. We accept the limitation and move forward. But the limitation has consequences. It means there are questions we can ask but never answer. What is the universe's true size? Is it finite or infinite? Does it have an edge or a boundary? What lies beyond the cosmic event horizon? Do the laws of physics apply there? Is there life in those regions? Are there structures or phenomena we cannot imagine because we have never observed anything like them? All of these questions are scientifically meaningful. They refer to objective features of reality, but they are unanswerable. The information needed to answer them is beyond the wall. This transforms large parts of cosmology from empirical science into informed speculation. We can construct models, we can make assumptions, we can calculate what might exist beyond the horizon based on extrapolating known physics. But we cannot test those calculations. We cannot confirm the models. The wall draws a line between what we can know and what we can only guess. And the wall is not the only one limiting our knowledge. Another boundary exists, closer and more familiar, but just as absolute. The cosmic microwave background surrounds us like a glowing shell. It is the most distant thing we can see with electromagnetic radiation, a snapshot of the universe at 380,000 years old. Before that moment, the universe was opaque. Photons could not travel freely. They scattered endlessly off free electrons in the dense plasma that filled all of space. This makes the cosmic microwave background an impenetrable barrier to light-based observation. We cannot see through it. We cannot image what lies beyond. It is a wall of light in the most literal sense. This wall is fundamentally different from the cosmic event horizon. The event horizon is a consequence of expansion and distance. It defines regions of space whose light cannot reach us because space expands too fast. The cosmic microwave background is a consequence of opacity. It defines a moment in time before which light could not propagate freely. One wall is spatial, the other is temporal. Together, they bound our observations in both dimensions. The cosmic microwave background was discovered accidentally in 1965 by Arno Penzias and Robert Wilson. They were testing a sensitive radio antenna and detected a persistent noise coming from all directions. The signal was uniform across the sky, unchanging day or night, season after season. After eliminating all possible sources of interference, including pigeon droppings in the antenna, they realized they were detecting radiation from space itself. The noise was the afterglow of the Big Bang. This discovery revolutionized cosmology. It provided direct evidence that the universe had a hot, dense beginning. It confirmed predictions made decades earlier by George Gamow and others, who had calculated that a Big Bang should leave behind a bath of thermal radiation. The temperature of that radiation, cooled by billions of years of expansion, matched observations almost perfectly. The cosmic microwave background became the most important piece of evidence supporting the Big Bang model. Satellites have since mapped the cosmic microwave background in extraordinary detail. The Cosmic Background Explorer, launched in 1989, measured its spectrum and found it to be a perfect blackbody, exactly what theory predicted. The Wilkinson Microwave Anisotropy Probe launched in 2001 mapped temperature variations across the sky to a precision of millionths of a degree. The Planck satellite launched in 2009 improved those measurements further, creating the most detailed image of the early universe ever produced. These maps reveal tiny fluctuations in temperature, hot spots and cold spots covering the sky at various angular scales. These fluctuations correspond to density variations in the early universe. Regions that were slightly denser appear warmer. Regions that were slightly less dense appear cooler. The pattern of fluctuations encodes enormous amounts of information about the universe's composition, geometry, and history. Cosmologists have extracted measurements of the universe's age, its matter content, its expansion rate, and more from these maps. The cosmic microwave background is a treasure trove of data, but it is also a wall. The surface of last scattering is the moment when photons decoupled from matter and began travelling freely. Before that moment, photons were trapped. Any light emitted earlier was absorbed and re-emitted countless times, thermalized into the background plasma. The specific information about what emitted that light was erased. All we see is a uniform glow with tiny density-driven fluctuations. We cannot see individual structures. We cannot see stars or galaxies because none existed yet. We cannot see through the plasma to earlier times. This creates an absolute limit on electromagnetic astronomy. No telescope, no matter how powerful, can image the universe before recombination using light. The universe was opaque. Light did not escape. The cosmic microwave background is the earliest photograph we can ever take with photons. Everything before it is hidden behind a glowing curtain of plasma. Cosmologists have proposed alternative methods to probe earlier times. Neutrinos decoupled from matter much earlier than photons, roughly 1 second after the Big Bang. A cosmic neutrino background should exist, filling space with relic neutrinos from that era. Detecting these neutrinos would allow us to observe the universe at 1 second old, far earlier than the cosmic microwave background permits. But neutrinos interact so weakly with matter that detecting them is extraordinarily difficult. The cosmic neutrino background has never been directly observed. Experiments are being designed, but success is not guaranteed. Gravitational waves offer another window. Primordial gravitational waves generated during inflation or the first moments of the Big Bang could still be travelling through space. Unlike photons and neutrinos, gravitational waves are not absorbed or scattered by matter. They propagate freely regardless of the universe's opacity. Detecting primordial gravitational waves would give us 1 second, potentially as early as 10 to the negative 35 seconds if inflation occurred. The search for primordial gravitational waves focuses on their effect on the cosmic microwave background. These waves would create a specific pattern in the polarization of the microwave radiation, a signature called B-mode polarization. Several experiments have searched for this signal. In 2014, the BSEP-2 experiment announced a detection, generating enormous excitement. But follow-up analysis showed the signal was contaminated by dust in our own galaxy. The detection was not confirmed. The search continues. Even if we succeed in detecting the cosmic neutrino background or primordial gravitational waves, we only push the wall back slightly. We do not eliminate it. Neutrinos were particle interactions to occur. Before that, even neutrinos could not propagate freely. Gravitational waves from inflation tell us about the inflationary epoch, but not what came before or what caused inflation. There are limits beyond which even these exotic signals cannot penetrate. The ultimate wall is the Planck time. Quantum gravity effects dominated. Our current theories break down. We cannot describe what happened. We cannot calculate observables. General relativity and quantum mechanics are incompatible at those scales, and we have no unified theory to replace them. This is not just an observational wall. It is a theoretical wall. We lack the physics to understand the earliest moments. Some speculative theories attempt to describe the Planck era. Loop quantum gravity suggests space-time is discrete at Planck scales, made of tiny loops of space. String theory proposes that fundamental particles are actually vibrating strings in higher dimensional space. Both theories modify physics at extreme energies and might allow calculations of what happened near the Big Bang. But neither theory is confirmed. Neither makes testable predictions we can currently verify. They remain mathematical frameworks, not established science. The cosmic microwave background wall is therefore not the deepest barrier. It is the earliest we can observe with established methods. Deeper walls exist at earlier times, blocking access to the universe's first moments. We are layered in boundaries. The cosmic event horizon limits us spatially. The cosmic microwave background limits us temporally to 380,000 years. The cosmic neutrino background, if detected, would limit us to 1 second. Primordial gravitational waves, if found, would limit us to inflation. The Planck time limits us theoretically. Each wall represents a threshold where observation or understanding becomes impossible with current knowledge. Each marks a boundary of the knowable. We can push against these walls with new technology and new theories, but we cannot eliminate them. They are features of the universe's structure, consequences of the physics that governs reality. We are trapped inside nested shells of ignorance, each shell hiding the one beneath it. And the outermost shell, the cosmic event horizon, is closing in. 100 billion years from now, the night sky will be empty. An observer standing on a planet in the Milky Way will look up and see perhaps a few dozen galaxies, the remnants of the local group that have merged together over time. Everything else will be gone. No distant galaxies, no quasars blazing across cosmic distances, no galaxy clusters or superclusters, just a handful of nearby structures and then nothing. Darkness. Infinite empty space stretching in every direction. This is not because those distant galaxies will have died. They will still exist, still forming stars, still evolving, but they will have crossed the cosmic event horizon. Space will have expanded so much that their light can no longer reach us. They will be causally disconnected, separated by a gap that no signal can cross. From the perspective of that future observer, those galaxies might as well not exist. They will have vanished behind the wall. The cosmic microwave background will also be gone. Right now, it fills the sky with microwave radiation at 2.7 Kelvin. But expansion redshifts that radiation to longer and longer wavelengths. The temperature drops. In 100 billion years, the cosmic microwave background will have cooled to a tiny fraction of a degree above absolute zero. Its photons will be stretched into radio waves so long and weak that they will be undetectable above the background noise. The afterglow of the Big Bang will fade into invisibility. This creates a devastating scenario for future science. Imagine a civilization that arises in that distant era. Perhaps on a planet orbiting a red dwarf star, one of the long-lived stars that will still be burning when most others have exhausted their fuel. That civilization develops astronomy. They build telescopes. They look out at the universe to understand their place in the cosmos. What will they find? They will see their own galaxy, or rather the merged remnant of the Milky Way and Andromeda, and the other local group members. They will see a few neighbouring dwarf galaxies, gravitationally bound and close enough to remain visible. And beyond that, nothing. Empty space. No matter how far they look, they will find no other galaxies. The sky will be dark. Without distant galaxies, they cannot measure cosmic expansion. Hubble's law depends on observing that distant galaxies recede faster than nearby ones. If all galaxies are local and gravitationally bound, there is no recession to measure. The civilization will have no evidence that space expands. They might conclude the universe is static, unchanging, eternal. Without the cosmic microwave background, they have no evidence of the Big Bang. That uniform radiation is the smoking gun, proving the universe was once hot and dense. Without it, the Big Bang becomes just one hypothesis among many. They might develop alternative cosmologies, a steady-state universe, an eternal cosmos with no beginning, an island of matter in infinite empty space. All of these models would fit their observations because their observations would be so limited. They would have no way to measure the universe's age. Current methods rely on cosmic expansion and the microwave background. Without those, age becomes guesswork. They might study stellar evolution and estimate how long stars have been burning, but without a larger cosmological context, they cannot determine whether their local cluster is young or old compared to the universe as a whole. They would have no knowledge of dark energy. Dark energy is detected through its effect on cosmic expansion, making distant supernova dimmer than expected. Without access to distant supernova, the civilization cannot discover acceleration. They might not even realize dark energy exists, even though it still fills space and still drives expansion beyond their visible horizon. They would be cosmologically blind, not because they lack intelligence or technology, because the universe has hidden itself. The walls have closed in. The information needed to understand cosmology has been redshifted into oblivion or pushed beyond the horizon. Their science would be fundamentally limited by their era. They would be like scientists trying to understand oceanography while living in a desert. The evidence is gone. This scenario is not speculation. It is the inevitable consequence of accelerating expansion. Dark energy is pushing space apart faster over time. The cosmic event horizon is shrinking in moving coordinates. Galaxies that are currently visible will fade and vanish. The process has already begun. We are living in a transitional era, a brief window in cosmic history when the universe is still largely observable. Before us, the universe was smaller and everything was closer. After us, the universe will be emptier, and most of it will be hidden. Our era is privileged. We can see the cosmic microwave background. We can observe distant galaxies. We can measure expansion and discover dark energy. We can piece together the universe's history from the Big Bang to the present. Future civilizations will not have this luxury. They will inherit a cosmos that has erased its own evidence. They will be stuck in permanent ignorance, unable to discover truths that are obvious to us. This raises a disturbing question. Are we in the same position relative to earlier eras? Is there information that was once accessible, but is now lost to us? We observe it at this specific moment in its history. What if earlier observers, hypothetical civilizations billions of years ago, could see things we cannot? What if the universe was more transparent, more revealing, when it was younger? There is some evidence for this. The cosmic event horizon was larger in the past when expansion was slower. Galaxies. Early civilizations could have observed those galaxies. They could have measured their properties, studied their evolution, learned from them. That information is now locked away, inaccessible to us. We have lost it. Not because it was destroyed, but because it moved beyond the wall. The early universe was also denser. Galaxies were closer together. Interactions were more frequent. Star formation was more vigorous. Supermassive black holes grew rapidly by accreting gas. All of this activity happened in regions we can still observe, but we see it only as it was billions of years ago. The current state of those regions is hidden. We cannot know how those early processes concluded. We see the beginning and middle of stories, but not the endings. Therefore, every era has limited access to the universe. The observable universe changes over time. Early observers see different things than late observers. Some information is available only briefly before it slips beyond the horizon. We are not at the end of this process. We are somewhere in the middle. We have already lost access to some regions. We will lose access to more, and future civilizations will lose access to nearly everything. This creates a hierarchy of cosmic knowledge. Civilizations that arise early, when the universe is young and dense, have access to rich data about structure formation and galaxy evolution. Civilizations that arise in the Middle Era, like us, can still observe the Big Bang's afterglow and measure cosmic expansion. Civilizations that arise late, in the far future, are left with scraps. They live in an emptied cosmos where most evidence has vanished. If we could communicate with a civilization from the distant future, we could tell them things they could never discover on their own. The universe expands. It began in a hot, dense state. Dark energy accelerates expansion. Billions of galaxies exist beyond your horizon. These facts would be revelations to them, impossible to verify but consistent with physics they could test locally. They would have to take our word for it. They would be relying on testimony rather than observation. It does not just block our view, it blocks everyone's view, eventually. The universe is structured so that most of its contents become unobservable given enough time. Expansion and acceleration erase evidence. Information is redshifted into invisibility or pushed beyond horizons. The cosmos hides itself layer by layer until almost nothing remains visible. We are watching this happen in real time. Every year, distant galaxies fade a little more. Every decade, the cosmic microwave background cools slightly. Every million years, another galaxy crosses the event horizon. The universe is in the process of vanishing, and there is nothing we can do to stop it. The wall is closing, the darkness is spreading, and in the end, only a tiny island of matter will remain visible, surrounded by an infinite ocean of emptiness that we know exists but can never see. Stars will die, galaxies will fade, black holes will evaporate. Given enough time, every structure in the universe will dissolve into radiation and empty space. This is not dramatic catastrophe. This is thermodynamics. The second law demands that entropy increases, order decays into disorder, complexity simplifies, energy spreads out until it becomes so diffuse that nothing interesting can happen anymore. The universe is running down, and the wall of light ensures we will never see most of it reach that final state. The timeline is almost incomprehensible. 100 billion years from now, most stars will have exhausted their fuel. Star formation will slow dramatically as galaxies consume their reserves of hydrogen gas. The universe will be populated mainly by red dwarfs, small stars that burn slowly and can last for trillions of years. White dwarfs, the cooling remnants of sun-like stars, will dominate. Neutron stars and black holes will lurk in the darkness. The era of bright, luminous galaxies will be over. By 1 trillion years, even red dwarfs will begin dying. The last stars will flicker out. Galaxies will go dark, containing only stellar remnants. White dwarfs will cool into black dwarfs, inert spheres of carbon and oxygen that emit no light. The universe will enter what cosmologists call the degenerate era, named after the degenerate matter that makes up white dwarfs and neutron stars. Nothing shines, nothing burns. Dead stars orbit silently in dead galaxies, but even dead stars do not last forever. On timescales of 10 to the 30 years, stellar remnants will evaporate. Gravitational interactions between objects in a galaxy occasionally accelerate one object to escape velocity. It gets ejected, flying off into intergalactic space. Over immense timescales, every object in a galaxy except those very close to the central black hole will be ejected this way. Galaxies will dissolve, their contents will scatter into the void, the black holes remain, they will be the last massive objects, the final gravitational anchors in an increasingly diffuse universe. Black holes grow by accreting matter, but in the far future there will be almost nothing left to accrete. They will sit in empty space, isolated, dormant, and then they too will die. Stephen Hawking proved in 1974 that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now called Hawking radiation. This radiation is extremely faint. For a black hole the mass of the Sun, the temperature is, the radiation is far too weak to detect, but it exists, and it carries away energy. Over time, the black hole loses mass, it shrinks. The evaporation process is incredibly slow. A solar mass black hole takes 10 to the 67 years to evaporate completely. Supermassive black holes, millions or billions of times more massive, take even longer, 10 to the 100 years or more. These timescales are so vast that calling them long is meaningless. They dwarf the current age of the universe by factors of trillions upon trillions. But eventually every black hole evaporates. The final burst of radiation as the black hole reaches zero mass would be spectacular, a brief flash in the darkness, and then nothing remains. After the black holes evaporate, the universe enters its final era. The black hole era gives way to the dark era. Space contains only photons, neutrinos, electrons, positrons, and other stable particles, all spread out so thinly that interactions between them are extraordinarily rare. The temperature of space approaches absolute zero. The cosmic microwave background, already undetectable by this point, continues cooling. Its photons stretch to wavelengths measured in light years or more. Effectively, the radiation ceases to exist as anything meaningful. Dark energy continues driving expansion. Space grows. Particles drift farther apart. Distances between any two particles increase without limit. Eventually, every particle in the universe is causally disconnected from every other particle. Each exists in its own isolated pocket of space-time, unable to interact with or even detect anything else. The universe becomes a collection of infinitely separated points, each completely alone. This is heat death, maximum entropy. No gradients exist. No energy flows from hot to cold because everything is uniformly cold. No structure remains, no complexity, no information, just an endless, changeless void where nothing happens and nothing can happen. The universe reaches equilibrium and stays there forever. But we will never observe this. The wall of light ensures it. The cosmic event horizon already blocks our view of distant regions. As time passes, that horizon shrinks further. In 100 billion years, we lose sight of everything beyond the local group. In 1 trillion years, even the local group has merged into a single dark remnant. We are left observing a tiny island in an infinite ocean. The final stages, the evaporation of black holes and the approach to heat death, occur so far in the future and at such vast distances that they are completely hidden. We can calculate what should happen based on thermodynamics and quantum mechanics. We can model the universe's far future, but we cannot observe it. The information never reaches us. The wall blocks it. This creates an asymmetry in cosmic knowledge. We can observe the past in great detail. We see the universe as it was billions of years ago by looking at distant light. We can trace its history from the Big Bang forward through structure formation, galaxy evolution, and cosmic acceleration. We have a rich understanding of where the universe came from, but we have almost no observational access to where it is going. The future is hidden behind the wall. We rely on theory and extrapolation. We assume the laws of physics we have discovered will continue to apply. We assume dark energy remains constant and continues accelerating expansion. We assume black holes evaporate as Hawking calculated. These are reasonable assumptions based on current knowledge, but they are assumptions. We cannot test them observationally on cosmic timescales. The experiments take trillions of years, and we will not be around to see the results. This makes eschatology, the study of the universe's ultimate fate, fundamentally different from cosmology's study of the universe's origin. We have direct evidence for the Big Bang. Measure the abundances of light elements created in the first few minutes. We can observe distant galaxies and trace how structure formed. The past is written in the sky, and we can read it. The future is blank. We know the universe is expanding and accelerating. We know galaxies are moving apart. We can calculate forward and predict heat death. But we cannot confirm the prediction. We cannot observe the universe in 10 to the 100 years. The wall prevents it. We are making claims about the far future based on theories we cannot fully test. We believe those theories are correct, but belief is not the same as observation. Some physicists speculate about alternatives to heat death. Perhaps dark energy decays or changes over time, halting or reversing acceleration. Perhaps new physics emerges at extreme timescales, physics we have not discovered because it only becomes relevant after trillions of years. Perhaps the universe undergoes phase transitions that reset the clock, allowing new structures to form even after stars die. These ideas are speculative. They might be wrong, but we cannot rule them out observationally. The wall hides the evidence. The wall of light is therefore not just a barrier to seeing distant space. It is a barrier to seeing distant time, both past and future. The cosmic microwave background blocks the past before recombination. The cosmic event horizon blocks the future beyond 100 billion years. We are trapped in a narrow window, a brief moment in cosmic history where the universe is partially visible. Before and after walls surround us. This is the universe's deepest truth. It is structured to hide itself. Expansion creates horizons. Opacity creates barriers. Quantum uncertainty creates limits on measurement. Time creates inaccessibility, both backward toward the Big Bang and forward toward heat death. We're embedded in a cosmos that reveals only a fraction of itself, and that fraction is shrinking. The walls are closing, the light is fading, and in the end, we will be left in darkness, surrounded by a universe we know exists but can never see. The wall of light is not a single boundary. It is nested walls, layered barriers, concentric shells of unknowability. Each wall represents a different limit. Each blocks a different kind of information. Together, they define the maximum possible extent of human knowledge about the cosmos. We can push against them with better technology and deeper theories, but we cannot break through. The walls are built into the structure of reality itself. They are features, not bugs. The universe is designed by physics and mathematics to be partially hidden. We live in the age of visibility, a brief era when the cosmos is still observable, still knowable, still accessible to science. Before us, the universe was opaque. After us, it will be empty. We stand in a narrow window, looking out at a universe that is already beginning to disappear. Every photon we collect is a message from a region that may already be beyond the wall. Every observation is an act of salvage, retrieving information before it is lost forever. This is why we build telescopes, why we launch satellites, why we map the cosmic microwave background and measure distant supernovae and search for gravitational waves. Not just to satisfy curiosity, but because we are running out of time. The universe is hiding itself, and we are the last generation, or among the last few who can see it clearly. We are witnesses to a cosmos in the process of vanishing, and once it is gone forever. The wall of light is absolute. The darkness beyond it is permanent, and we are on the wrong side watching the light fade, knowing we can never cross.